Okay, so now we're going to be doing membrane channels and pumps. We had kind of touched on some of this in the previous ones, right? And so that you're going to see that more and more now that we have sort of a base built up. A lot of the things we used in chapter 4 are the ways we proved the stuff we're teaching now, right? And a lot of the ways that these things are going to be those connecting parts between the transcriptions, translations, etc., right? Okay. Okay, now your membrane pumps. Again, this right here is going to be your pumps, channels and pumps, membrane channels and pumps. And we can actually see we're isolating these things and working with them. Okay, now there's 3 classes of membrane transporter proteins. The membranes are going to be made permeable by the 3 classes of transporters. Now, keep in mind that they already are semi-permeable. They're permeable to things like water, CO2, etc., right? But these are going to be regulated in their permeability, i.e. made more permeable to certain substances by these 3 classes of transporters. Those 3 classes are the pumps, carriers, and channels. I hope you've all heard of that before to some degree. Okay, I'd be so disappointed in the biology classes if you haven't. Like, really make fun of them. Oh, Chris is gonna get it. Okay, now, so the transport of molecules across the membrane may be active or passive. Lipophilic molecules are going to be molecules that can pass through the cell membranes because they dissolve in the lipid bilayer. Simple diffusion will be the process by which lipophilic molecules move across the membrane down a concentration gradient from regions of high to low concentrations. Now remember, when we say that they can dissolve in the lipid bilayer, that does mean in the specific conditions we're looking at, right? Okay, so for water example, it normally cannot dissolve in the lipid bilayer, right? But under the massive overconcentration of water, where most of your surroundings is water, you can actually get it starting to dissolve and moving through the lipid bilayer, right? And that's a concentration gradient that's causing that. The passive active transport, again, we're going to have the facilitated diffusion. This is going to be the process by which polar molecules are transported across the membrane down a concentration gradient by a specific channel. Now notice these are all what types? Active or passive so far? Passive, yeah. We're not actively putting in energy, right? The energy is coming from somewhere else. Specifically concentration gradients or the fact that there are okay with binding to lipids, right? Okay, now the active, this is also typically called passive transport because the energy driving the ion movement is going to originate from the ion gradient itself, and so we are not giving energy in this. With active transport, we will actively be supplying the energy, right? What terminology is this all related to in terms of chemistry? This is going to be your delta G's, right? Okay, so keep that in the back of your head. It's going to be related to your delta G. That's what's going to determine whether you could do a passive or active transport, okay? Okay, so your active transport is going to be the process by which molecules are transported across the membrane against a concentration gradient. This is going to require the input of energy from another source. Again, think of it like this. It's all equilibriums, right? In a passive or facilitated diffusion process, you're going to have it where you are going the direction the equilibrium wants to go to establish itself. Okay? These are spontaneous processes. This is non-spontaneous process. You're pushing it against the gradient. Okay? You're pushing an equilibrium out against the equilibrium. Okay? Is that making more sense? Fantastic. Now, the transports of solutes and ions across membrane is going to pose an energetic cost. This is actually the concentration ratio across that membrane. This would be your delta G. And what do you notice about this? As we get things more and more concentrated on one side, what happens? Yeah, it shoots up, right? We need more and more energy to push to get more of that concentration there, right? You already knew this. It's the same thing as if you were trying to pressurize something. So if you're taking a hand pump and trying to pressurize something, what happens? Eventually it gets really hard to pump, right? That's because your energy is skyrocketing, isn't it? Yeah. This is, again, the membrane potential. This is in millivolts here. That literally is, do you guys remember your voltage from Gen Chem and maybe physics? Do they do voltage in physics here? Somewhat? Really? Okay. Anyways, I always have trouble with that because the school I went to, the 3-semester physics rotation was done in 2 semesters. So I actually kind of don't intuitively know which one is which. Yeah. Anyways, again, as you get a greater potential, you're going to be pushing against that potential, right? And so your energy to push against it's going to increase. Does anybody have any questions here? No? This is really straightforward energetics like we looked at before, right? But thank God we had a review on energetics, didn't we? Yeah, that's what that was for, by the way. So the free energy required to move an uncharged solute from side 1 of a membrane, where it's present at concentration of C1, to side 2 of the membrane, where it's present at concentration C2, would be given by this formula right here. That's actually the same relationship you're seeing here, right? Notice, if you were to write a linear regression for this, what would it look like? Y would be equal to delta G, right? The slope would be what? RT. Okay, and if you wanted it to be linear, it needs to be the natural log of C2 over C1. Okay? Okay, and so this actually is the formula. Notice that at a concentration where your y-intercept would be, this could be like a 0, right? Okay, so this is your gas law constant here. It's in kilojoules, by the way, and that's what your energy is going to be in. The temperature needs to be in Kelvin because of your gas law constant. Okay? Typically, this would be the absolute scale for temperature for your gas law constant. By the way, I don't know why your book does this. It does this a lot. This degree is actually wrong. So if you ever see that where it has an R with a degree in it here, what do Kelvin, okay, so degrees Fahrenheit, degrees Celsius, those are non-absolute scales, right? They're relative scales. Kelvin doesn't have degrees. It's an absolute scale. You don't have an arbitrary 0. Okay? So, anyways, it doesn't really matter. Your book does it because it's the degrees Celsius changes and Kelvin changes. Whenever you have change in Kelvin, change in degrees Celsius, it doesn't matter either way. You can use both. But it really does matter here. Okay? So be careful about that. Your book does that. It plays tricks with it, and you can catch you out. Okay? Really badly. All right. Now, the active transport, this is going to have a positive delta G. The passive transport has to have a negative delta G, right? Because, again, you're going along with spontaneity with the passive. Active transport, you need to push it against the spontaneous process, right? Or otherwise, you are non-spontaneous. What's the other word for non-spontaneous? In an equilibrium, what does that mean? It is spontaneous in the reverse. Exactly. Very good. Okay, so the electrochemical potential, your membrane potential, the sum of the concentration and electric terms. The free energy that's required to move a charged species from side 1 of a membrane to side 2 of a membrane would be given by this. Notice that's basically the same thing, but in these cases, you also have a charge potential, right? Okay, as you build up charge, that's going to start pulling the opposite charge from the opposite side, right? Okay, so you have another term here that's important, which is this right here. Z is going to be the electrical charge of the species. For example, phosphates oftentimes have a -2, right? That would be that -2 there. The F here is actually the Faraday constant. Again, that is a constant. Faraday's constant. Named after Faraday, by the way. The delta V here is going to be the potential voltage across the membrane. Please note that this is oftentimes just referred to as delta E. So yes, it's the voltage potential, but oftentimes they just call that the delta E for the like EFF, electromotive force. Okay? Okay. Does everybody kind of remember that from Gen Chem? Is that going to get anybody? Okay, so we have two families of membrane proteins that use ATP hydrolysis to actively transport ions and molecules across your membranes. Most animal cells will contain a high concentration of potassium and a low concentration of sodium. What do you notice about the charges here? They're both positive ones, right? And this is why they're used as an exchange for each other. What would that do to this right here? It would help to minimize that, right? Yeah. Okay. And so you'll have a low concentration of your sodium, high concentration of potassium in the animal cells relative to the external medium. The energy is required to generate these gradients, of course, because you're still pushing across your concentration equilibrium, aren't you? So pumps are going to be membrane proteins that are going to catalyze the active transport of ions against their electrochemical gradients. There are many, many uses for this, by the way. We'll get into a few of them a little bit later. But first, I want you to understand how they work, okay, and the underpinnings of them. So this right here is the sodium-potassium ATPase. Another way of saying this is pump, sodium-potassium pump, okay? More correct, though, ATPase. It's really informative, isn't it? What does this do? You have sodium being exchanged for potassium. Uses ATP as the energy source, right? Yeah. The name is fantastic, right? Tells you everything you need to know. So again, that's going to be the enzyme that hydrolyzes ATP. This will generate the sodium-potassium gradients across your membranes. The hydrolysis of ATP only occurs when the sodium and potassium are present. Thank goodness. That would be a freaking disaster if it just continuously chopped up ATP, right? This requires magnesium 2+, like almost all of the ATP enzymes, right? Typically that's used to bind to the ATP so you can actually do something. The 3 sodiums and 2 potassium ions are going to be transported per catalytic cycle. This is the reason I said minimize that term, not get rid of it. How'd you like it? Nice, right? Delta G for this is going to be 41.7 kilojoules per mole. So this is the P-type ATPases. They're going to be a family of ATPases that are going to form a phosphorylated aspartate intermediate. Another name for that is phosphoryl aspartate, which you can tell because it's just phosphoryl and then aspartate joined together. The examples of this include things like the sodium-potassium ATPase, of course. That's why it came up here. The saccharoplasmic reticulum calcium ATPase, abbreviated SERCA, because that's long. And biochemists and chemists are lazy, which is just how that works. The pump calcium 2+ out of the cytoplasm and into the sarcoplasmic reticulum of your muscle cells. The gastric H+ to potassium K+ ATPase. Again, this is going to pump the protons into the stomach. This is what's causing your stomach to be a lower pH at about pH 1. Okay. This right here is the phosphoryl aspartate, by the way. Again, that's the aspartate that's been phosphorylated, right? Okay, fantastic. So pumps exist in 2 conformations. One with the ion binding site facing into the cell, of course. One with the binding site facing out of the cell. The delta G of the ATP hydrolysis is going to be coupled to the interconversion of the 2 conformations to pump ions across the membrane. And this is what that looks like. So notice we're having the 2 forms, the 2 conformations going back and forth. Okay? Note that it actually looks like well, there's several different types of pumps you can make, but looks like an actual pump, right? They use like pump water or something, okay? Like you can make a pump that looks just like that. Right. And see how you got that? This right here is facing, in this case, out of the cell. We'll call this out. We don't have any label. We input energy. It causes this to rock the other way, and then it will release it into the cell, right? And then it will go the other way, and so on. Reset, pump, reset, pump. Okay, so the Circa, this is a single 110 kilodalton polypeptide. It contains a transmembrane domain consisting of 10 alpha helices and sites for 2 calcium 2+ ions. Contains a large cytoplasmic headpiece that has 3 domains. There's the N domain that binds the ATP, the P domain that accepts the phosphoryl group on a conserved ASP residue. The A domain, please do not confuse the A here with the ASP and ATP and all that, okay? Kind of easy to do. Anyways, the A domain links the changes in the N and P domains to the transmembrane part of the enzyme. And so this is what this actually looks like, by the way. So this is the transmembrane domain. What does transmembrane mean? Yeah, across membrane, like transport, transmembrane, same root, right? This is the A domain here. Remember, this is the one that links these, okay? Please, again, be careful. I know that the other ones act on ATP and ASP, and so it's easy to mess that up, okay? But the A domain is going to link changes in your N and P domains right here. This is your P domain, by the way. This has the ASP right there. Can you see that okay? That we were talking about. And so remember, that's going to be where you accept that phosphoryl group onto that ASP there. Okay. And then this is the N domain. And the N domain is going to be the one that will bind the ATP. Okay, it's right there. Okay, this right here is actually the calciums in here that are going to facilitate, that are binding in this facilitated transport. Okay? I shouldn't say that. That are binding in this active transport. I was trying to say it facilitates the process of this active transport. I don't use facilitate in this. It's just going to cause more confusion. So again, this is an active transport. We have ATP being bound in here. We're going to pump the calcium across, right? And this is where the calciums are actually being bound and are going to be moved one direction or the other. Okay, so this is actually, again, the calcium binding sites here that are going to be disrupted. The N and P domains have closed around your phosphoryl aspartate analog in this case, so we can actually vision this. The analog will be better at binding this so it doesn't get released as fast, right? So we have a better chance of seeing it. So this is actually shown as the Circa without the bound calcium 2+ and with phosphoryl aspartate analog in your P domain, which can allow the this to hold. So step 1 of this mechanism for Circa is going to be the calcium binding to the unphosphorylated Circa from the cytoplasm. This will be confirmation of E1 bound with the calcium, and notice the 2 number here because we need how many calciums? 2. Yeah. Note the parentheses in here are actually important. Why is that important? Are the calciums bound to each other? Yeah, binding 2 individual calciums, right? Yeah. So step 2 is the ATP binding. So you got your ions bound. Now we can bind ATP. Why don't we bind ATP first? Yeah, at that point you're providing energy, aren't you? It would be like hooking your electricity up without having your monitor on your phone. It's a lot of trouble and a lot of things could happen, right? It's not a good idea. Okay, so this is going to cause that rearrangement of the NP and A domains. This will actually trap the calcium 2+ ions, and exactly. You'll notice the energy almost always comes after binding what you're going to work with. Okay? And it may be involved in resetting it, but it's never going to just attach for no reason. Again, this conformation at this point would be the E1, the enzyme again, the calcium 2+, again, 2 of them on there, and there's an ATP now. The ATP will have the cleavage in step 3, and that'll be the transfer of the phosphoryl group to the ASP351. And that is going to be where that moves the phosphoryl group. I wanted to say facilitates this reaction, but that's a bad idea. Active. The conformation is your E1, P, calcium 2+, 2, and then ADP. What's this P stand for? Yeah, the phosphoryl group, right? Yeah, we phosphorylated that ASP. Okay. I know that it can get a little confusing because there's also a domain, P domain, right? But yeah, this was not a great naming job, whoever did this. But the ADP gives you a lot of clues there. Okay, so now we're on step 4. So at this point, we've done the transfer of the phosphoryl. This has provided that energy. Now we can start doing our next step. So ADP is going to be released, and we're going to have reversion. This is interconverting the E1 to the E2 conformations. So at this point right here, this is going to release your calcium 2+ on your opposite side of your membrane. So essentially what we've done, we had it like this, closed, right? And now we've chopped that up. That's going to allow us to open it up and release the calcium on the other side. Okay? Now note the E2, this is now the E2 which is open to the outside, right? Okay. And so step 5 is going to be the hydrolysis of your phosphoryl aspartate residue. This is going to release the inorganic phosphate, and so notice the P now disappears. And at this point, we're just left with E2, right? We've released everything else. All we need to do now is to revert and reset. So we're going to now, step 6, this is going to be reversion to prepare for a calcium 2+ binding from your cytoplasm. And so literally, we're opened, we release that phosphoryl, it can now flip. Okay. Yeah. Yep. Binding calcium in the cytoplasm and releasing it out. Okay, so the this is the overall diagram, by the way. I know that the overall diagram does a better job of understanding these things, but you kind of do need the steps, right? This mechanism likely applies to other P-type ATPases, including the sodium-potassium ATPase, with only a little bit of modifications here and there. But we have to actually look at them individually and do the studies to do that, right? And so that's a lot of work. This is the one that got it. Okay? So here we go. Again, this is that step 1. We're binding the calciums. So we're the E1 complex at this point, the enzyme. And again, this is going to be your cytoplasm right here and your membrane lumen on the other side. Okay? Okay, now, this is then going to uptake the calciums from the cytoplasm. At this point, we are going to be the E1 that's bound to the calciums. You can see those calciums bound there. Okay, step 2 is going to be attaching the ATP. Notice the A and P, the P portion changed now, and we have closed off so we can no longer release those calciums back into the cytoplasm. Okay, at this point we have the E1 calcium ATP complex. Now, what's going to happen step 3 is this is where we're going to transfer that phosphoryl group from the ATP to the ASP here. That's that one right there. And that will be the inorganic phosphorylation right there, and then the ADP. Okay, so at this point we've successfully trapped that, and we can only go one way in that reaction essentially without reassembling the ATP, right? Okay, and so at this point we have this long complex. It's fairly easy to remember as long as you understand what the parts here are, okay? Which is E1, P, calcium, and then ADP, right? And you can actually work yourself through this in this mechanism by that naming. If you forget one or don't remember the other. So right here, the next part is we now are going to release ADP. We're going to release the calcium into the outer channel. This will give us our E2P. This right here allows it to collapse that direction. Okay? Anybody have any questions about step 4? Okay. Now remember, that is to the membrane lumen. In this case, though again, this is a generalized, you can generalize this to any p-type probably. Okay? They're probably basically all the same, right? Of course, not calcium in those cases, but you get the overall gist, right? Ions. Okay. This right here then is going to be on step 5, the release of the inorganic phosphate. This will be a hydrolysis, by the way, meaning you're using up water to do it. This will give you the free enzyme 2. Step 6, you're then going to have reversion. So it's going to revert back to your form that you started with to do step 1, right? Where you bound the calcium. Again, this is going to have the cytoplasm being the one that can be fed in now. Okay? Anybody have any questions? No? Okay. Okay, so Digitox is going to specifically inhibit the sodium-potassium pump. This is actually going to work by blocking its dephosphorylation. So cardiotonic steroids, these are going to be potent inhibitors of the sodium-potassium pump. Some examples are digoxin and ouabane. I always have trouble with that. That's my accent. The ouabane, okay? Ouabane. Anyways, inhibits the dephosphorylation of your E2P form of your ATPase when applied extracellularly. When you get into med school and you have to start sounding smart, or otherwise people won't trust you, look it up and practice saying it, okay? It helps if you're in front of a mirror, so you can see how your muscles move. Anyways, I only have to appear so smart. Okay, now this is again going to be used to treat your congestive heart failure. It's going to decrease in the sodium gradient, results in slower removal of the calcium 2+ from the cell. An increase in the cellular calcium 2+ is going to enhance the contractile ability of your heart. This actually is digoxin right here. And again, that's that cardiotonic steroid. And again, this is going to inhibit this process right here. Okay? So remember where we had that phosphoryl release, dephosphorylation? That's what it's inhibiting. Okay? Okay, so foxglove is actually a naturally occurring source of digoxin. This is inhibition of the sodium-potassium pump again, diminishes the sodium gradient, results in a slower removal of a calcium 2+ from our cytoplasm. The increase in the intracellular calcium 2+ is going to increase the force of contraction of your heart muscle. This right here is what foxglove looks like, by the way. Okay? If you're wondering, it actually is part of a family, and that family has about 2,000 years of history as use of different heart medicines, but also as poisons, of course, to try to kill people. You can use any medicine as a poison, or poison as medicine for that matter. Just the dosage, right? You all heard that saying? The poisoner's model? Okay, good. The P-type ATPases are going to be evolutionarily conserved, and they're going to play a wide range of roles. So your yeast has 16 p-type ATPases that will transport ions. This ranges from things like H plus to calcium 2 plus to sodium plus transport metals like copper 2 plus, phospholipids with amino acid head groups also can be included. The human genome actually encodes 70 p-type ATPases. They all use free energy from ATP hydrolysis to drive membrane transport via conformational changes induced by addition and removal of your phosphoryl group at a key ASP residue. And again, that's a key residue because you can easily phosphorylate that bond. Where's my A? There it is. Okay. Notice again, that's that phosphoester linkage, right? Very easy to make in organic chemistry. Very easy to make in biochemistry. Okay. Okay, so multi-drug resistance actually highlights a family of membrane pumps with an ATP binding cassette domains. So the multi-drug resistance is going to be a phenomenon by which the development of resistance to one drug actually makes the cells less sensitive to a range of other compounds. So your multi-drug resistance is typically called MDR, the abbreviation, protein. The protein that acts as an ATP-dependent pump that extrudes a small amount of molecules, including drugs. It contains 2 membrane-spanning domains and 2 ATP-binding domains. Yes, it does look like a cassette, okay? But we'll see that in just a bit. ATP binding cassettes, or ABCs, it's such a great naming. ATP binding cassettes, ABC, right? ATP binding domains of the MDR proteins. Again, these will be the MDR cassettes right here. Again, remember they have the 2 ATP binding domains. Those are going to be the ATP binding cassettes, which are the ATP binding domains. Okay, now the ABC transporters are going to be transporters that include your ATP binding cassettes. And this is what they look like. So the eukaryotic ABC transporters, they're going to encode on a single polypeptide chain. They're generally going to export molecules from inside your cell. The prokaryotic ABC transporters, they're going to be made up of multiple subunits. They're often going to import specific molecules from outside of the cell. So there's actually quite a difference between eukaryotic and prokaryotic, though the overall mechanism of activity doesn't really change that much. It's more of how you code for it, how you assemble it, and then how you, whether it comes in or out, right? Which side of it is exposed to which direction. Anyways, these are the MDRs right here. And so this right here is actually your membrane spanning domain right there. Again, that's the membrane spanning domain. Notice yellow being the membrane spanning domain, matching yellow in the membrane. Okay. The ATP binding cassette is right here. This is the portion that's going to bind the ATP. Again, that's the blues right there. This is the N terminus. This is the C terminus. Okay. Everybody good with that? Okay. This right here is actually the bacterial one. This is specifically the bacterial lipid transporter, or MSBA. Remember that this is actually made of multiple subunits, not a single one. Okay? This is just one subunit, right? So see this little bridge here? That's just one amino acid polypeptide, right? Okay. And just keeps going. That's why we only have one N and one C. This one right here, this is actually 2 subunits. See that? Okay. And so you have an N right here. This is then the membrane spanning. This is the ATP binding cassette right here. And notice we would have 2 of these fragments then that are being made. Everybody okay with that? Okay, I know that we kind of have a weird thing going on because they're so conserved. We have like an overall mechanism. And then you could have 70 different ones that are all the same thing. They just bind different stuff. Okay? They look very similar. They have very similar conserved portions. They basically, the only really difference you get is slight difference in sizes of where they bind and how they bind exactly. Okay? But the overall mechanism, same thing. And then you have this, which is 2 subunits versus 1 subunit, but still has the same damn mechanism, right? But it's same mechanism, so you need to just understand them as one set. Okay? Okay. So again, this is your ABC transporters. They're going to have that significant conformational change upon ATP binding here. So this is actually going to be the open form of these. And again, you can notice actually these look a bit like cassettes, okay? If you look really closely. But here's the P-loop, by the way. Can everybody see that P-loop okay? Which, whenever you're talking about ATP binding, what do you always end up with? Some sort of P-loop, right? Because you need something to interact with phosphates. So this will be your open form. Notice that what are we exposing here? We're exposing the inside of this membrane spanning domain so we can load stuff up. We're also exposing our ATP, aren't we? Okay? Or we could deposit stuff, right? One of the two. This right here is your cell exterior. This would be your cell interior. Again, this is the membrane spanning domain. Okay, this will then be the closed form. So what's going to happen is your ATP is going to bind here in these 2 spots. This is then going to cause it to close so it binds the ATP fully. Okay? At this point, we have the closed form that has the ATP. This is also a conformation of the closed form. Can everybody say okay? What's happened here is this group right here has done a conformational interchange, a rotation. See, that's just a rotation. And that rotation, everybody's used the sliding folding door things. Especially like, have you ever seen one of those desks that slide up? Okay. This kind of looks like that, right? Yeah. So it kind of opens up by sliding into each other. Okay. And that's what you're seeing right here. Again, that is the closed form still, though there is an opening to the cell exterior at this point. Still considered the closed form because it's closed around the ATP, right? Which is the ATP bound form, and this part right here is still closed. Okay. Okay, so let's talk about the different steps of this process. Again, this is the mechanism and needs overall with the steps fully explained, and then we'll look at some figures. The step 1 is going to be the transporter of of ATP, and substrate is then going to open the channel towards the inside of your cell. Please keep in mind that there is a difference between eukaryotic, prokaryotic, right? Okay. Which side is here? We'll look at the mechanism first and do this in one go, and then we'll talk about that stuff. So the transport of free ATP substrate opens channel towards the inside of the membrane. Step 2, the substrate binds. This is going to induce a conformational change in your ATP binding cassettes. This will increase the affinity of the ATP. Again, remember, bind the thing first that you're going to transport, then get the ATP, right? Okay. And that is cooperative. It is more, it is energetically favorable now to bind the ATP, right? Okay. Step 3 is going to have the ATP binding, where it's going to lead to the opening of the channel to the opposite face of your membrane. This one was towards the inside of the cell. Now it's open to the what side? Outside, exactly. Step 4, this is going to be release of your substrate to the outside of the cell. These always end up as different steps, by the way. Though, to be honest, typically they would be pretty right one after another, right? But if you were to look at them in an energy diagram, you would have your high energy states, and then you'd have your intermediates for each of these steps, right? Okay. Now, this is going to be the overall process as we looked at before. And so right here, what we see is this is step 1 now. At this point, we have the cell exterior closed, the cell interior is open. And so what's going to happen is our substrate is going to insert, bind. This is going to increase the affinity of this binding site here for ATP. We're then going to have 2 ATPs loaded into those 2 sites. Okay? Once we've loaded those ATPs, they're going to induce a conformational change that's going to release our substrate to the outside. Then what's going to happen is our substrate will detach and drift away. Okay? This will leave that binding site empty. At this point, our ATP are now less energetically favorable to be bound there, right? Because we're no longer binding substrate. And so now we can do a hydrolysis of that higher energy ATP down to ADP. This is going to help reset this mechanism. Okay. Did that make sense to everybody? Okay, did I lose anyone there? Fantastic. Any questions so far? No? Okay. Okay, so the lactose permease, this is going to be an archetype of secondary transports that will use one concentration gradient to power the formation of another. This is the secondary active transport. That's what that's called here. That process by which the thermodynamically unfavored flow of one species up a concentration gradient can be coupled to the favorable flow of a different species down a concentration gradient. Basically, you're using one concentration gradient to power the other, right? The carriers are going to be proteins that transport species across the membrane without ATP hydrolysis. This may be called secondary transporters or co-transporters if they move species uphill by a secondary active transport. Remember, again, this is a type of active transport. Why is it active transport? Not using ATP in this case. What are we using instead? A concentration gradient. Same thing as battery. Okay? That's how actually batteries work, in case you're wondering. We build up concentration of a charged species on one side, and then we let that concentration relax, and that's how we end up providing the power. Okay? And so when you recharge like a lithium battery, like a chrome battery, you're literally moving lithiums up on one side to increase the concentration on one side. Well, a specific form of lithium. Anyways, very, very similar to batteries. Okay? Okay, so this is actually, again, your classes of carrier proteins. We have the antiporters. Anti meaning what? Opposites, right? Yeah, so you're going to have 2 things moving in opposite directions. So again, antiporters are going to be secondary transporters that transport substrates in opposite directions. We have symporters. These are going to be, again, secondary transports that will transport substances or substrates in the same direction. Sim meaning like sympathetic together, right? Okay. And so symporter moving together, right? Antiporter moving opposite. Like antipathy. Excuse me. Okay. Uniporters. What do you think that means? Unit, like unicycle. By itself, right? So uniporters, this can be the carrier that transports a substrate in either direction based solely on the species concentrations. Basically, it just moves it back and forth across here. Okay? And it just does one species. This is the lactose permease. So the lactose permease is an E. coli transporter. This uses the H+ gradient that's generated by the oxidation of fuel molecules to drive the uptake of lactose and other sugars. Contains 2 domains that are joined by a single polypeptide. And so right here, again, we have the extracellular, the periplasm. Here we have the cytoplasm, intracellular. And right here, we actually have that binding site in the middle so you can actually see it. Okay? Typically, how these work in almost all of their cases is, remember how an enzyme or a catalyst typically works. It breaks up a high energy step into multiple lower energy steps, right? Okay. One of the ways you can do that is basically by putting a site in the middle where it actually would bind okay. So it literally takes the species most times, it binds it in the middle somewhere, and then it unbinds on the other side, right? And that gives you lower energy steps. Okay? Okay, so step 1 is going to be the transporter with a binding pocket facing outside, and your cell binds a proton from outside the cell. Step 2 is once it's protonated, the transporter binds substrate from outside the cell. Step 3, the transporter everts, meaning it changes configuration, right? Okay. Step 4, the transporter releases the substrate to the inside of your cell. Step 5, the transporter is going to release the proton to the inside of the cell. And then step 6, the transporter everts to complete the cycle. And right here we have it. Again, this is the lactose 1 that we're looking at, though we're using the lactose 1 to help us understand an overall type, right? Okay. And so right here, we actually have that lactose permease. By the way, the name being fantastic, right? Works on lactose. It does what? Increases the permeability of your cell membrane. It's an enzyme, right? Okay. So again, what type is this again? It has two things that are going which directions? Together, right? And so it is a sympore. Yeah. Okay, and again, that's the proton and lactose. The proton is driving it. That's the energy. Okay, it's literally an electrical energy, battery energy. Okay, or you can think of it as diffusion energy, right? Okay, and so it's going to drive it across the membrane. Right here, we actually see the process. This is a carboxylate. It's going to take on a proton here. The lactose is then going to bind in the second step, right there. This is going to be eversion. Frankly speaking, sometimes they'll say reversion. I'm sorry. It's like a Freudian slip that's very hard for me to not do. Okay? Because really, they mean almost the exact same thing. Okay? It's just technically it's not a reversion because it doesn't go back to the exact same state. Okay? So it would actually be an eversion or evert. Right? I think I did it previously. I'm pretty sure I did. Yeah. Very hard not to do. Anyways, this has now done the eversion. This is going to be inside the cell at this point. You're going to release the lactose into the cell. And then your H plus is going to be released into the cell. That's step 5. This will convert that back to the carboxylate. You will then do another eversion, step 6, in which case you get the carboxylate exposed to the outside of the cell again. And we reset. Okay. I believe it's time. You all have a wonderful day, and I will see you on